Which of the two sets listed here do you think has a greater number of elements? The set A consisting of 0, 5, 10, 15, in other words counting from 0 by 5s, or the set B consisting of 0, 2, 4, 6, 8, and so forth, counting by 2s. Now there are two ways to think about this, and we want to get precise about exactly how we can answer this question. One way is if you graph these sets on a number line, it seems pretty obvious that the set A, which consists of 0, 5, 10, and so on, as opposed to the set B, which is 0, 2, 4, 6, 8, 10, and so on. It looks like on any segment of the number line, this set is going to have more elements than this set. And in that case, you would want to say that there are more in this set than there are in this set. There certainly are more on any segment of the number line. Now that's really not quite true. Let's say on any segment of length greater than 2 on the number line. Okay, if the length is greater than 2, then this set has to have at least as many as this does. And actually I'm going to change that statement. Let's say the length of the segment is greater than 4. If the length of the segment is greater than 4, then there will be more elements in this set than in this set. Not going to prove that, but you can think about it, and I think it'll seem fairly obvious if you think about why that's true. The whole point is, that's a fairly precise statement there, but the point is that if you look at a chunk of the number line, as long as that chunk is fairly long, this set's going to have more than this. We could look at short chunks where we just, between 4.5 and 5.5, this set doesn't have any, and this set has 1. So you got to be careful about that. But you see the idea that these are denser than these, or appear to be, so that set B seems to have more. Okay? That's one argument. The other argument is that these sets are both infinite, so how could one have more than the other? Okay, how could one infinite set be bigger than another? Doesn't infinite mean just plain old infinite? Okay. Now it turns out that there are flaws in both of these ways of looking at the situation. And the way we decide to think about this is as follows. Well, we can match the elements of this set with the elements of this, can't we? We can come up with a rule that matches each element of A with an element of B. Now, I didn't write the next element of B. It's 20, and it would match up with 8. And you could actually come up with a formula for associating one of these with one of these. If N stands for any number, 0, 1, 2, any counting number, 0, 1, 2, 3, 4, 5, I'm sorry, any whole number, 0, 1, 2, 3, 4, 5, then we're going to associate 5n in this set with 2n in this set. Okay? Because if n goes 0, 1, 2, 3, 4, 5, then 5n goes 0, 5, 10, 15, 20, and 2n goes 0, 2, 4, 6, 8. So we just associate the nth element of this set with the nth element of this set. If we went out to the 10th element in A, there'd be a 10th element of B that we could associate with it. So we can match these sets up, and it's therefore very hard to say that one set's bigger than the other. I mean, if they match up item by item, and if you can give a rule for matching up, then you have to say they're the same size. Okay? So, we can do a one-to-one correspondence, which is what I just described. And if there is a one-to-one correspondence, the sets are going to be said to have the same cardinality. And that might seem inconsistent with this argument, and it is if you want to take this argument. Since the number line goes on forever, we're going to be able to do this matching. The matching, if we had to draw it here, we would do this, then we would do this, then we would do this, and this line's going to get more and more horizontal because these numbers are going to go out further and further than these are. But we're never going to run out of these numbers, and we're always going to be able to match these. So since we can match the two sets, we're going to say that they have the same size despite what this looks like.